All right, welcome everybody to week 15, day 2. We just did an hour of lab time essentially for probability. And let's just go through the answers here. So your name, of course, should be Bill Kearney. Favorite topic from CSI 26. Sarah put down hash tables. That is, in fact, the right answer. Hash tables are the best topic in CSI 26. Although graph theory is probably a close second as well. So let's go through the answers, and looks like you guys are mostly getting it right. Okay, so the expected value of 1d10. So what does 1d10 mean? It means you roll one 10-sided die. Okay, that's the terminology there. And so the expected value is 5.5, because that's the average of 1 to the raised 7, 8, 9, 10, right? Divided by 10. The sum of all numbers from 1 to 10 is 55, divided by 10 is 5.5. So if the expected value of one die is 5.5, if you roll two of them, the expected value is going to be 11, right? And so one trick that I use is anytime I have an even number here, what I do is I divide the even number by 2, and that 10 becomes an 11. So it becomes 1 times 11, or 11. So the average value of 10d6 is the same thing as 5 times 7, which is 35. That's a little mathematical trick that I use a lot for these things. So 100d6 is going to be 50 times 7, which is 350. And I could probably prove to you why that works, but I think you can see right here. Yeah, 5.5 times 2 is 11. And yeah, so every 2 dice is 1 higher than the number here. And that's just kind of how the algebra on that works out. Doctors say this one graph theory algorithm. That's funny. Dijkstra's is pretty important. Yeah, so I've got this Dijkstra's one. I might turn it into like a computational geometry problem. That was what KR at UNCC suggested to you guys, was to do convex holes. So basically, given all the cities in America, make a convex hole, which is a polygon that encloses all of them. So that's pretty important for a lot of things, actually. Very useful in computational geometry then. Okay, so the expected value of 2d10 is 11. Expected value of 1d20 is 10.5. 10d6 is 35. 100d6 is 350. That's a 3 there. Okay. Any questions about this part? Nope. Okay. Imagine a cheater die where 3 has been replaced by a second 6. The expected value is going to be 1 plus 2 plus 6 plus 4 plus 5 plus 6 divided by 6. So that's 9, 13. 13 plus 11 is 24. So 4. Okay. What are the odds of rolling 2 or less on this dice? This is a CDF question now. So you could do the probability distribution function, which is the odds of getting a 1, a 2, a 3, a 4, a 5, and a 6. And all of these are going to be 1/6, 1/6, except 3 is going to be 0, and 6 is going to be 2/6. That's 1/6, 2/6. So this would be what's called a PDF. Not this kind of PDF, right? Portable document. No, this is a probability distribution function. And so if we have no 3, but a second 6, then the odds of getting 1 are 1/6, 2 is 1/6, 4 and 5 are 1/6, 3 is 0 because there are no 3's on it, and the 6 is 2/6 because there's 2 of them. And so the CDF is going to be the integral of this. And so it's going to look like this. that's at 1 up here. Okay, and that would be the CDF, which is the cumulative distribution function. And then you can just look at the CDF and answer these questions from it. So the odds of rolling 2 or less are 2/6. Odds of rolling 3 or less are 2/6. 5 or less is 4/6. 6 or less are 6/6, or 1. Okay. Imagine I have 4 cards numbered from 1 to 4. I draw a card at random. What are the odds the second card's going to be higher than the first card? Okay, so this is when things start getting a little tricky, right? And in real life, a lot of these probability questions start getting really, really tricky. And you end up having to like write software to like do a Monte Carlo simulation to simulate all the different possibilities. And in this case, it's still simple enough that we can actually kind of sketch it out. So the probability tree. So for our first draw, we have 4 possibilities. You get a 1, a 2, a 3, and a 4. Okay. And then for each of these draws, we want to write down how many different ways we could we could either draw all 16 possibilities, but I'm just going to draw the ones in which we win. We win when we draw a second card. It's higher than the first. So a 2, a 3, and a 4, a 3 and a 4, a 4, and there's no way of drawing higher than a 4. So we've got 1, 2, 3, 4, 5, 6 different ways. We have 6 ways of beating our first card out of a possible 16 possibilities. Because there's 4 different outcomes for the first one, 4 different outcomes for the second one. There's 16 total possible outcomes. We could draw this on a grid if we wanted. 4. And rather than doing like a sum, we can just like show which ones. This is the first draw, this is the second draw. First draw is a 1, second draw is a 2. These win, and that wins. And so there's 16 possibilities, 6 of them win. The odds are 6/16 or 3/8. Okay, and the reason why I like doing this is because this was actually one of the questions that was on my final, and it was more complicated than this, but basically it was the same question, just with more possible cards. I think it was just for a deck of cards, right? And for a full deck of cards, you don't want to sketch out the entire probability tree, right? So what you want to do is just try a smaller example that you can solve by hand and see if there's a pattern, right? And so the pattern would be for a 13 by 13 is it's going to be half, but with the diagonal taken out, right? So you're like, okay, that I can see the pattern here. It's okay, you know, and you sort of work it out. You're like, okay, if it was 13 by 13, you got ace, 2 all the way down through king, you know, and it's going to be not the diagonal, but everybody north of the diagonal. And so it's going to be 13 squared is the field. So that's what, 169 possibilities. There's 13 along the diagonal. So that's 158 divided by 2, 79. So it's 79 out of 169. So that's the odds of drawing a second card that's higher than the first card from a deck of cards. You see, yeah, and if I went too fast, that, I mean, I was sitting there on the final, like, just like sketching this out, like, okay, what's the pattern? How do I do this? You know, but yeah, if I doing the mental math correct, which, you know, who knows? 13 squared, 169. Okay. Minus 13 along the diagonal, divided by 2, 78. 78. 78? No. Oh, 100. Yeah, see, I did the math wrong. Okay. So 6. 78. There. Yep. Is there a formula? That's the thing. Like everyone wants a formula. You know what I mean? Like, and if you read probability textbooks, like there's going to be formulas for all sorts of things. You know, if you have an urn of balls and you pull 3 out and replace 2 of them and draw a third one, well, that's the Helmholtz formula. You know, and the reality of the situation is, like, for any sort of like, and those, it's all well and good for like basic problems. Like if you draw a card and replace it, what are the odds of getting a higher card, which is what we're doing here, right? Ooh, actually, I probably should have mentioned this is with replacement, right? If you don't have replacement, then the odds are going to be different, you know. And so I should have mentioned with replacement, right, where you put the card back and then you draw again. If you don't, then you can't get a diagonal, right? Because you can't draw the same card at the same time. So the reality is that there aren't always formula. There's formulas for all the basic cases, and then for more complicated things, you can use those formulas for like the simple stuff. And sometimes complicated problems are based on simple problems, but a lot of times you just have to sit there and work it out, you know. And so you have to find the pattern and extend, you know. So if this one didn't have replacement, then if you drew the 1, you couldn't get a 1 again. And so if you drew a 1, it's a 100% chance this time of getting a 2, 3, or 4. And if you drew a 2, you couldn't get a 2 again. So there's a 1 out of 3 chance you go lower. There's a 2 out of 3 chance you go higher. And so if you have no replacement, without replacement, then it's 50-50 that the second card is going to be higher. Okay. And so, you know, the question is, like, after you pull the card out, do you put it back in and draw again? And if you put the card back in, then if you get a tie, you don't win, right? So the odds of winning are lower. So. All right. You assume there's another replacement, then did you get 1/2, Aries? Yeah, you're correct. Yeah. It's my bad for not being clear on that. Not like these are graded anyway. I mostly just wanted to give you guys hands-on time, because it's one thing to sit there and watch somebody do stuff, you know, in an online lecture, and you're kind of like sitting there like, oh, okay, that makes sense. It's a whole nother kettle of fish when you need to do it yourself, you know what I'm saying? So I always try to give you guys hands-on time. Okay. Imagine I have 10 cards numbered from 1 to 10. Draw a card at random. What are the odds the second card is going to be higher than the first card? So this, yeah, okay, yeah, so yeah. Let's say there's no replacement. 1 out of 2 also, right? So, right? Because that's the pattern we found. If there's no replacement, it's 1 out of 2. If there is replacement, if you put it back in, then there is 100 possibilities. 1 to 10, 1 to 10. And that diagonal we lose. And so out of the 90, it's going to be 45. Okay. So there's 45 outcomes up here. And so it'd be 45 out of 100. Or, yeah. Whatever, if we simplify, but it's 45 out of 100 if with replacement. And it's 1 out of 2 without. Right. And so that was how I solved it on my final, was because it's too hard to draw out a probability tree for all 13 times 13 draws you can make, right? So what you do is you start with a smaller problem. It's the same approach we take in computer science, right? Like when you're trying to do the Bridges Mountains assignment, you know, if you tried doing it on these giant maps and they don't work right the first time, well, good luck, you know. So what you do in computer science when you're trying to test your code is you start with a small map. You start with a little 4x4 or 5x5, you know, and you build walls that are infinitely high or close to it, and you see if the thing can navigate around it, you know. So if 20 cards without replacement, the odds would still be 1/2. Yeah, the odds of getting a higher card are 50-50, right? Like, kind of makes sense. And so you find the pattern and you extend. That's the computer science way. Is you start small, get the small case working, and then extend it out and see what you can see. It's the same thing in probability. It's the same thing in programming. So, yeah, for any pattern, yeah, for any number of cards, it's going to be 50-50 if you pull the card out, right? Like, I mean, think about it. It's like you're going to get some card and the other card, you know. Extrapolation is bad. Well, yeah, she wasn't a computer science person then. Yeah. But yeah, like you find the pattern, you know, and extend. And it's a lot better, in my opinion, than trying to memorize all the different formulas, because life gets complicated real fast. If I roll 10 dice and select the 3 highest ones, what's the average roll? How would you guys solve that one? Well, let's do number 12 yet, and then we can talk about it. Because that's actually the dice rolling system for the role-playing game that I play. It's called roll and keep. You roll a certain number of dice, you keep the highest ones. So if you roll 6 and keep 3, you roll 6 dice, you keep the 3 highest. Right? What's the average? They're D10s. What's the average number? It's not immediately obvious. Let's just put it that way. It's not immediately. It's not like, oh, clearly it's this formula. Like, okay. So here we have a weighted average problem. So where'd my pen go? Make it a little easier for me. All right, so 1 times 0.1 is 0.1, 2 times 0.2 is 0.4, that's 4. 3 times 0.3 is 0.9, 4 times 0.1 is 0.4, 5 times 0.1 is 0.5, 6 times 0.2 is 1.2, 0.5, 1, 2.3, 3.3, 3.5. So, is that what you guys got? 3.5? Yeah, looks like it. Aaron got 1.2, looks like. Oh, no. He just cut off probably the bottom of it. That's for the 6. Okay. It's the same as a regular die. That is correct. So if I were to offer you, you know, your choice of which die to roll, you know, and you'd roll 100 of them, it doesn't matter. You know what I mean? Like, like the big thing about expected values is a lot of the times, instead of having this big complicated distribution and all this stuff, a lot of the times when you have an expected value, you just take, you got 1, 2, 3, 4, 5, 6, and whatever. You get rid of all that. You just say, no, it's 3.5. You just replace all of this randomness and stuff like that. You just say, I'm just going to treat it like it's a 3.5. And for a lot of purposes, not all of them, because like if I were to ask you who would roll higher, a regular die or this die, I would have to think about that. I'd have to think about if it was, if you roll 2 dice and see which one's higher. I would have to think about that. Might be the same, but I'd have to work it out. But for a lot of purposes, the expected value can just replace all the randomness. Instead of thinking of a d6 as a d6, think of it as 3.5, just a number. And it doesn't help. Like, let's say you're playing Dungeons & Dragons, right? And you're fighting a monster with 4 hit points. You kill them if you do 4, 5, or 6 damage. In that case, you cannot treat it as 3.5. Because if you treated the damage as 3.5, you'd say, okay, it takes 2 hits to kill the person. And it's a little more complicated than that. You've got a 40% chance of killing the person outright. You've got 30 plus 18, 48 plus 7%, 18%, 25%, 55%. 55% chance of killing it in 1 hit, or 40% chance of killing it in 1 hit. You have a 55% chance of killing it in 2 hits. You have a 5% chance of killing it in, no, that's off by a little bit, damn, in 3 hits, or more, right? And that's actually not quite right. It's a little bit higher than that. But that's just kind of an eyeball on it. Okay. And so when it comes to something like this, like how many hits does it take to kill something, you can't just use the expected value, because sure, that's your average result and maybe it's the most likely, but that doesn't tell me what I want to know, which is like, what are the odds I'm going to kill the person, or how many hits does it need to kill a person, so you can't always use the expected value, but for a lot of things you can just treat, I mean, it's still random, right? But for a lot of things you can just replace this random roll with the average, especially when you're doing a lot of them. Like if you're rolling like 100 d6 or something like that, you just be like, I'm going to do roughly 350 damage. Do you want me to roll it? And we would actually say that when we're playing Dungeons & Dragons. High level Dungeons & Dragons, I'm rolling 80 d6. Do you really want me to roll it and add it up? It's going to take me a while. They're like, no, just use the average. Okay. Well, how much damage is 80 d6? Do you guys remember? It's 40 times 7, 280. All right, take 280. Cool. If you fall off a cliff in Dungeons & Dragons, you take a d6 for every 10 feet you fall. The maximum falling damage is 20 d6, and so we would call it taking a 70. So like, I'm just going to step off the building and take 70 damage, because it's 20 d6, which is the same as 10 times 7, which is 70 damage. So at high level D&D, you got 500 hit points. You don't even care. Okay, I step off the building, I fall, I take 70 damage. Do you want me to roll it? No, it's fine. Just take 70. So, yeah, you can technically one punch them to death with 4 hit points. Exactly. So, 40% of the time you're actually going to kill them, and so it's a pretty big difference whether or not they survive a round. Because if they survive a round, they can hit you. So you really want to know, what are my odds I'm actually going to take the person out? And a lot of times you'll overkill. So like if somebody has 2 hit points, then you've got a 90% chance of killing them, but it's not 100%. Because there's a 10% chance you'll pip him, right? So in cases like when you're close to the edge, like when the monster has 4 hit points or 3 hit points, you can't really use the expected value. I mean, you can say on average I'll do 3.5, but a lot of times you have to actually say like, okay, what are the odds that I'm actually gonna, and then you use the CDF, right? In that case, it's like when you're kind of close to the boundary, you typically will actually look at the numbers. For large numbers, we typically just replace it with a mean. So we'll just treat 100d6 as 350 simply because you're going to have a Gaussian, and the Gaussian's going to be centered on 350, and most of the results you're going to get are going to be kind of near it. So, you know, if it matters, yeah, it matters. Like if you're fighting a monster that has 350 hit points, then I'd be like, all right, roll it. You know what I mean? Like if you're close to the expected value, I'm gonna go like, yeah, roll it. So we're gonna roll 100 die 6. Jeez, no, that's not helpful. Okay, 344, yeah. It's like if the monster had like 345 hit points, I would be like, roll it. Because if I just always give you if you're fighting a bunch of monsters that all have 345 hit points, and I let you do the average every time, you would one-shot them every time, right? And so I'd be like, roll it. You pull up a dice roller. Oh, 344, he has 1 hit point left. Alright, fine. Quicken magic missile. Nah, he's dead. Yeah. You guys kind of get me on this? Like, when it's like right near the edges, then you typically don't want to just replace with the average. But like if you're fighting a monster that has 3,000 hit points, I'd be like, yeah, just do 350. You know, I don't care. You know, it's not going to matter. Okay, that makes sense to you. So let's talk about roll and keep. Do I want to save? No, I don't. How would you compute that? So if we had now we're not doing Dungeons and Dragons anymore. We're now doing Legend of the Five Rings. So if you're gonna roll 2 dice and keep 1 of them, these d10s. So you're gonna roll a d10 and a d10 and keep the higher number. What's the average result? What's the expected value of 2 keep 1? You like the sunset? I like wallpaper engine. It's very nice. So, would we use a Gaussian curve? Yeah, you could. Like when the numbers get high enough, there's something called the central limit theorem, and the central limit theorem says that when you have a random process repeated an infinite number of times, it turns into a Gaussian curve. That's what a Gaussian is. A Gaussian is the sum of an infinite number of random processes. It's kind of the limit. As the number of rolls you make approaches infinity, it turns, you know, with 1d6, it looks like this, uniform distribution. With 2d6, it looks like a peak. And over time, the thing sort of, like if you look at the distribution for 3d6, it looks like this. So rolling a 10 or 11 is average. You see, it's already starting to look like a Gaussian. Yeah. So that's 1d6. This is 3d6, and then count 1s as 2s. If you get a reroll of 1 to 3 once, if you get a roll of 1 to 3 once, count 1s as 2s. So there's different ways that people allow you to do like character generation in Dungeons and Dragons, where like if you roll a 1, you can treat it as a 2, so you can't have really bad stats. Or you can re-roll one of your dice, you know. And so depending on how generous the DM is, you'll see the average moves from 10 to 11, which is average. The average will start sliding upwards depending on how generous the DM is on re-rolls, you know. You re-roll any one die, re-roll your lowest die, that kind of stuff. So, a 4 dice 6 drop lowest. Yeah, that's a pretty common system too. So, and it's similar to what we're doing right now with 2 keep 1. Like with 2 keep 1, you roll 2 dice and drop the lowest, right? With this, you roll 4 dice and drop the lowest, and so it changes the average from 10.5 up to 12.24. Okay? So it pushes the average up, so you get better stats on your heroic D&D character. So how do you come up with that 12.24? Right? Typically, you do it in a program. You'll typically, at a certain point, you're just like, this is too complicated for me to solve numerically. This one we can solve using our brains. But when it gets really complicated, we write a program and we roll tons of dice and we average the results together. Okay, so what is this? How would you guys solve this? It's very similar to what we just did. We've got 10 numbers. Should have drawn that square a little better. This is the first die. This is the second. The expected value of D10 is 5.5, right? So if you just use the expected value of the second die is the same, right? So you can't use it, right? Because you're just going to be like, all right, it's not going to help, but you can't use it here because it's actually a case where it matters. Like the second die might be bigger than the first. That's what we're doing with the cards. Pull a card out. Okay. So with two keep 1, let's say you roll a 7 and a 5. The answer of this is 7. If you roll a 2 and a 10, the answer to this is 10. Right? It's not a fraction. It's just, right? So you roll 2 dice, you keep the bigger one. Right? If you roll a 4 and a 1, you get a 4. If you roll a 2 and a 7, you get a 7. So what is the expected value of 2 keep 1? What do you think? How would you solve this? Anyone? Roll 2 dice and you keep the bigger. Or drop the smaller, however you want to put it. Well, let's work through it a little bit. If you roll 1 on the first die and a 1 on the second die, what's your result? What's your outcome? If you roll a 1 on the first die and a 2 on the second die, what's your outcome? We're not adding them this time. We're doing max. Okay. We'll roll 1 on the first die and a 3 on the second die. What do we get? 3. You guys starting to see the pattern here? So 4, 5, 6, 7, 8, 9, 10. What if we roll a 2 on the first die and a 1 on the second die? 2. 2 on the first die, 2 on the second die. 2. so on and so forth. So you add up all those results together, divide by 100, that's your average result. That's it. There's got to be a faster way. I don't know. You do it in a computer pretty quickly. So that's the simplest one though. Like now compute 6, keep 3. It's the average result for that. How many possible outcomes are there? Writing a program is usually the fastest way, and this is why I tell my math students, like, don't neglect computer science, because you're going to be doing a lot of it. How many different outcomes are there for 6, keep 3? For 2, keep 1, there was 100 outcomes, right? There's 2 dice. 10 squared is 100, right? And then we do the max of each of the... Basically, the outcome is going to be the max of the row and the column, right? Is each cell there. So what is the... How many different outcomes are there for 6 dice being rolled? Not 10 to the 3rd, 10 to the 6th. And what about for 10, keep 2? It's 10 to the 10th. If you want to compute an exact number, it's 10 to the 10th. It's a big number. Just to do the maximum. All right? So basically, you roll 10 dice, you take the 2 biggest ones. Okay. And so, I don't know, a person smarter than me might be like, oh, well, that's clearly the 7th Helmholtz function, and they have like some sort of like sigma, whatever, and it'll spit out the number. But here's the reality, is that the reality is even this is like pretty trivial as far as these things go. At a certain point, you kind of hit the limit as to what you can compute by hand. With this, I could probably compute this by hand. I'm already like halfway through the table. I could probably divide it along the diagonal and note that it's symmetrical, and so I could throw away half of it and divide it. You know what I mean? Like I could, because this is symmetrical, I only need to add up half of it and then multiply by 2. So there's computational tricks and things like that I could use, but even for this, I'd probably use a program, to make it. And then when it gets even more complicated, this is exponential. This is not cheap. Exponential is the devil when it comes to computer science, And so at a certain point, you lose the ability to just like compute answers. I don't know, dude. It's too complicated for me. What's the expected value? I don't know. Let's find out. Let's do this. All right. Let's do this. All right. So making a 10 by 10 array and a vector, and we are just going to fill it with the max of the row in the column, right? Just to humor me. Okay, so for size ti equals 1, I is less than 11, I plus I is less than the size, let's say, I plus plus, yyp equals, close off the braces, And then we will just say vector dot at I dot at j is equal to the max of I and j. Copy paste error. Let's fix that. Okay. And then we're done. We will see out the result for every row in the vector, for every column in that row. See out the column, followed by space, followed by a new line. And yeah, the zero row, I just put that in there so I didn't want to have to do like plus ones. Fine, I'll do it properly. There we go. So this is kind of what I was doing by hand over here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 3, 3, 4, 5, 6, 7, 8, 9, 10. Right? It's this table over here. Just done on computer. And this is why math people have to know computer science. Because if you did this by hand, there's a pretty good chance you would just probably screw it up. Looking at the pattern, it looks like there's a pattern here, right? It goes down with 7s and left with 7s. So there's 1, 1, there's 3 2s, there's 5 3s, there's 7 4s. So there's a mathematical pattern here, right? So it's 1 times 1 1 plus 3 2s plus 5 3s plus 7 4s, yeah. So you can probably compute this numerically for any size, but it's about to get more complicated because we're gonna do 3 dice now, okay? And yeah, it's gonna get more complicated. So the expected value of this, let's compute that, int sum, and so rather than out, I guess we can do that still. Sum plus equals call. And then we will see out sum divided by quantity size times size. And so the expected value is 7. So there you go. There's the answer. So I could use like my math skills to be like, oh, well, look, it's a pyramidal number and the sum of a pyramidal number. Like, nah, I'm just going to add them up, dude. You know, like, sometimes having the math under your belt will save you needless computations. You know, if you can recognize that it's like odd numbers times even numbers in a series, and like a lot of times there is a way of replacing that with something that's simpler to compute numerically. So don't think that I'm like dogging on math, because the more math you have, the better the code you will write, because you'll do less wasteful computations. But at a certain point, you're going to hit like your limit as a human, and so we rely upon computers to do arithmetic for us so that we don't make mistakes by hand. And then when it gets too complicated, we end up doing what's called a Markov, or not a Markov, a Monte Carlo simulation, where we just roll the dice. Like, we'll just roll 10 dice, keep the 7 highest, and just do that a million times. Okay, so so for example, if I wanted to make a table of all the different possibilities for roll and keep, roll 7, keep 2, roll 8, keep 5, you know, that kind of stuff. What I could do is just simulate each one of those processes a million times and then output the table as the result, you know? And if this is not quite accurate, then I could just do more rolls if I wanted, right? So I'm doing 10,000 rolls for each one here. Let's make it 100,000. And if that's not accurate enough, let's do 1,000,000 rolls for each one. Let's work that CPU, make it work for its money. Okay. So what's happening here? This is the number of dice we're rolling on the this side here. This is the number of dice we're keeping. So if we roll 7 dice and keep 4, the expected value is 33.73-ish. 33.7. You see, each time I roll it, get a slightly different number. Okay. And if you're going to be just using this table, then knock yourself out. Do 5 million computations per number, because you only need to compute this thing once. You only need to, if you're going to be playing the Alpha or role-playing game, you only need to compute this table one time, print it out, and take it with you to the table. Like, somebody will ask you, hey, what are the average odds? What's the expected outcome if I roll 6 dice and keep 3? You look at this, you're like 26.5. Right. All right. I'm trying to hit a 25 or better, so I probably shouldn't take any penalties on that. Okay, so I'll just roll 6, keep 3, and hope I hit. And you just looking at it, it's probably going to be a little better than 50-50 that you're going to hit if you're rolling 6, keep 3 against a TN of 25. Yeah. But all you have to do is you just have to run the simulation one time, and then you just print it, take it with you. So there's different rules, and I don't know which rules are being used here, but like a 10 will explode. So a 1 keep 1 is 6.1, because if you roll a 10, it explodes. You set the 10 aside, you roll another die, and add the result to 10. So if you roll a 10 and then a 5, you get a 15 on one die. And that's why we're not seeing a 7 as the result for 2 keep 1. It's because we're using a different rolling system, where if you roll a 10, it explodes. And again, that's something you can't, it's hard to compute directly because it's infinite, possibly, right? Because you can keep rolling 10s. And so there's 1 out of 10 chance you roll a 10 every time. So pretty accurate, 100K. Yeah. So 6.11, 6.11, 6.10, 6.14. Yeah, so 6 keep 3 here is 26.61, 26.57, 26.53, 26.54. You can see they're all kind of in the same ballpark, And as you roll more and more dice and average them together, you get more and more accurate numbers. There still might be a little bit of error, but who cares? Who cares? And so what I did for this is, so 5 million times. Right. 5 million times. I got here my table, and I call a function called roll multiple times. And so, because that's the off by 1 thing, right, that I had before. So roll multiple, it's going to say like roll 6 and keep 3 or whatever. Okay. And what it's going to do is rolls number of times. So 5 million. So 5 million times it's going to do the roll and keep. 5 million times it does it. And then it divides the result by 5 million. So it's an average. So 5 million times it adds the numbers together and then divides the accumulated sum by 5 million. Okay. And this will work until you integer overflow, somewhere in the billions, but at that point I would probably switch to a long or CPP int, So do you guys see this though? This is kind of the point I'm trying to get at today. Is that in computer science, we can do a Monte Carlo simulation. We're like, I don't know what the answer is. It's too complicated. So I'm just going to do it. I'm just going to roll the dice and keep the highest. And you can see how I do this down here. I make a vector, and I have a function to roll a die. And so, if I'm rolling 10 dice, then 10 times I roll a die, and then I sort it highest to lowest, and I pick off just the, like if I'm rolling 10 and keeping 2, then the keep would pick out the top 2 and add those together. Right? So this is how you would implement roll and keep. So you roll 5 dice and keep 4, So it makes a vector of size 5. It populates that vector with random d10 numbers, and sorts them greatest to smallest, and then adds the top 4. And there's probably better ways of doing this. I probably shouldn't be using a vector, for example, because it's allocating off the heap millions and millions of times a second. This is really not the most efficient way of doing this. I should probably just have an array of size 10, because who cares, You know what I mean? It really shouldn't be a vector, because it's doing a lot of wasteful heap allocation and stuff. But who cares? It works. And the speed doesn't even matter, because, like I said, I only need to run this program one time in my life. And then after that, I just print out the answer. There it is. In fact, on my computer, I found somebody who had done this. Let's find out if they... does an accuracy depend on random? Yeah, it's random. It is random. And the quality of your random number generator does matter as well. Let's see here. So I found somebody who computed these odds, right? And this 1 to keep 1 is an odd, is 60. Oh, it's a 60% chance. This is a percentage chance. So this is different. Okay, yeah. So this is the odds that you beat a target number, and that's different from what I did. I was computing the average. I was computing the average expected value. This is if you roll 6 keep 3. What are your odds you hit an armor class of 25? 6 keep 3. Yeah. That's what we said, right? It was a little bit better than 50-50. 6 keep 3 is a standard attack roll when you're starting off. And most monsters that you're fighting, when you're starting off, either have an armor of 15, 20, or 25. And so if you're fighting someone with an armor class of 20, you have an 82% chance of hitting. If they have a armor class of 25, which is high for a new player, you have a 50-50 chance of hitting. And then if they go up to 30, then you only have a 30% chance of hitting. That kind of sucks. So somebody like heavy armor and high reflexes, you're going to have an annoying time fighting them. And then you could look at this and be like, all right, I just got some experience points. I want to level up. If I put another point into swordsmanship, I'll go from 6 keep 3 to 7 keep 3. And then you just look at this. You're like, okay. So against somebody with an armor class of 25, I'll go up from a 51% chance to a 60% chance. Cool. Against somebody with an armor TN of 30. Yeah, okay, all right. Seems like a worthwhile purchase. And if you want to make a bigger purchase, you can boost your agility up, and that would take you from 6 keep 3 to 7 keep 4. And that would boost your chance from 51% to 85%, which is a huge jump in power, right? And for hitting somebody with an armor class of 30, you go from a 30% chance to a 63% chance. But that purchase would be like, you play 4 games, so 16 hours of gameplay, and that would take you from 6 keep 3 to 7 keep 4. Whereas going this way from 6 keep 3 to 7 keep 3 is 1 game. So you have to think about it. You're like, do I want to save up my experience for 4 games and be kind of mediocre for 4 games to get this giant boost in power after 4 games, or I play 1 game and make this move here, and then maybe I save up for 4 games because I'm going to be 10% better at kind of everything, and then I go up to 8 keep 4, and that's here. And then I have a 91% chance of hitting the person. That's a total of 5 games of experience. So seeding with time, I am seeding with time, I think, right? So it doesn't actually matter, because when you're rolling 5 million times, everything averages out. You know what I mean? It actually doesn't matter. if you seed or not. Watch, if I don't seed, I'm gonna get the same numbers because you're rolling 5 million times. It actually doesn't matter if you're randomizing it properly or not. It'll matter if you're rolling like once, because you're always going to get a 3 or whatever, you know. But when you're rolling 5 million times, they all average out. Look, all the numbers are exactly the same. Oh no, that one's off by 0.1, which, yeah. You know what I mean? You know what I mean? That's the thing about random numbers, that when you roll a lot of them, details actually stop mattering very quickly. So the actual bottom level here, D10, it rolls a random number from 1 to 10, and if I got a 10, then it explodes. So if I got a number less than 10, it just, like I roll a 7, return 7. If I got a 10, then I return 7 plus, and then I roll again. And so it's a recursive function, which is highly unlikely to stack overflow, because you would have to explode, 30,000 times in a row, which is fantastically unlikely. But technically, this could technically stack overflow you in a 1 out of the heat death of the universe number of times. Fantastically unlikely, though. So it's not something I even worry about. Okay, so yep, that's the whole size of the program, and this is what we do. Like, this is like if something gets too complicated for us to handle, we just write a little program. All right, I'm dumb. Let's just write a program, and we'll just do it and just average the results. This thing right here is the important thing. 5 million times we do a trial, and we average it. What's the average result of this trial? That's it. That's the expected value. Okay. You guys cool with that? Yeah, here's somebody generated those numbers. So 2 keep 1 is that 7 that we computed, right? Because that's with your 10s not exploding. The 10s do explode, you get an 8 on average. They don't have any decimals on here. And like I said, there's different rules. Like, if you get really good at swordsmanship, your 9s and 10s can explode, which is, it's a nice jump in power. If you're talking about 6 keep 3, if you get the thing where your 9s and 10s explode, it goes from a 24 to a 31. Like, that's like a almost 50% boost in power, right? So yeah, there's different ways the dice can explode. And like I said, my brain is just not powerful enough to compute. Like with Hungry Blade, it explodes on 8, 9s, and 10s, but only one time. And I like, my brain is just like, no, I can't do that. I can't do that in my head. I'm sorry, So 6 keep 3. If 8s, 9s, and 10s explode once, this is 34. Yeah. So 10 keep 10 on a regular die is 61. We got a 61. 85. 8 keep 5 is 41. 8 keep 5 is 41. Yeah, so they got the same numbers as me. Cool. Good to know. And the reality is, you don't even have to do it 5 million times. Like, you can see the numbers were pretty accurate well before that. But for me, the main question is, when do I get bored? Like, if I'm going to be printing out this chart and taking it with me to a table, I'm perfectly willing to let it run for like a couple minutes. Like, I'll just go and get a glass of water and come back. Okay, there are the numbers. I only have to run this program once, so I might up it to 20 million. But you're at that point, you're just talking about like error margins that are like, yeah, minuscule anyway. All right, hang on one sec. All right, so that's me, you know, and mostly I do this because I'm too dumb to figure it out directly. I have a friend who's an actuary. He plays L5R with me, and a lot of these things he can like just do in his head. He's like, yeah, it'll be 7. You know, he's got all these mental tricks and all this kind of stuff. Actuaries are people who do this kind of stuff for a living, right? So all the examples we typically give are from like role-playing games and gambling and stuff like that. But in real life, there's people who make their money computing this kind of stuff, and they're called actuaries. Well, there's also casinos. You know, a croupier, right? Do you guys know what an actuary works for? Who they work for? Insurance, yeah. So, let's say somebody comes to you, McCohen, and you're working for some life insurance company. You're working for McCohen Life Insurance, and the person's 60 years old. They got diabetes, and they have a broken leg. And they say, I would like to purchase $500,000 worth of life insurance. How much do you sell them that policy for? It's gambling, right? It's gambling. They're gambling, they're going to die. Like, let's say 10-year term life. So let's say they're 60 years old. If they die before they're 70, they win. If they live to be 70, you win. So, how much you sell them the policy for? They got diabetes, they're 60 years old, they're overweight, high blood pressure, they have a broken leg. So the actuaries are the people that make the insurance industry go. They compute tables of odds for common cases like diabetes and high blood pressure and overweight, things like that. They have all these tables of like people dying, right? And they will sit there and say, this person has a 33% chance of dying from the current day to 10 years out. And so if you're the company, you're like, all right, well, they have a 30% chance. Let's say, let's make the numbers even. Let's say they're buying $500,000 worth of life insurance, and they have 1 out of 5 chance of dying. So that means the expected payout to them is $100,000. Did you guys hear that? It's literally gambling. You're gambling with your life. You're gambling you're going to die. And the reason why you do that is not for you. It's for your kid, your wife, or whatever. You know. So you gamble that you die, and if you win, you're dead. So you didn't really do that well, because you're dead. But your kid's going to be able to go to college or whatever. You know what I mean? So let's say that they're going to buy $500,000 worth of life insurance. 10-year term. So from age 60 to 70, if they die, they win $500K. All right. So let's say you compute the odds of them dying at 20% or 1/5. Right? So the expected value of this life insurance policy, the expected value of it is $100,000. You're expecting to pay out $100,000. This number here comes from the actuary. And if they get it wrong, your company could quite possibly go out of business. Because people will buy the life insurance policy that is the cheapest. So if you overestimate or underestimate, your company goes out of business. You guys understand? Because if you don't charge enough, then you pay out more than you take in, and you go bankrupt. If you try charging too much, they buy a policy from somebody else, and you go bankrupt. It's very, very important for actuaries to do a good job. And life is complicated, and things like pandemics throw a monkey wrench into everything. You know what I mean? So it's really, really important that you come up with a good number here. How much are we expecting to pay out to this person? They're 60 years old, they have diabetes, a broken leg, high blood pressure, overweight. All right, they have a 20% chance of dying. mortality risk. Okay, they're buying $500,000 of insurance, 500,000 times a fifth. We're expecting to pay out $100,000 on this. Okay, it sounds like actuaries are underpaid. Oh no, they are not underpaid. Actuaries make bank. They make bank because the entire insurance industry rests on their shoulders, right? They live a very nice life. It's hard to become one. So my friend lives in LA, and he runs the Dungeons and Dragons down in LA. 82,000? That seems low. But yeah. Actuary 1. Actually sounds quite low to me. It sounds closer, but it's at least from what I've seen from my one of my buddies was studying to become an actuary for a while. Like they make bank, and that's because you got to get the good ones. What does it take to be one? Study probability and statistics. That's what it all is. It's all probability and statistics, and a lot more than the 2 weeks that we're going to spend on it in this class. Let me tell you, I'm just giving you kind of like the brief idea of it. So if it's $100,000 expected payout, the margin you're supposed to make as a life insurance company is 10%, right? So you have to charge, say, $110,000, right? And so you're going to charge the person. You're going to quote them $110,000 over 10 years. That works out to $11,000 per year, or a bit less than $1,000 a month. Yep. So you're going to charge them 11/12, like $900 something a month. Yep. $917 a month. So you say, all right, sure. Here's your quote. And they're like, nah, it's expensive. How much is $100,000 of insurance? That's a lot of money, So, yeah, sorry, you got diabetes, you got a broken leg, and things like diabetes will probably be in actuary tables. Things like having a broken leg or like missing an eye, like that kind of stuff's not. There's usually not that much data on it, and that's where the actuaries come in. A lot of times, like they got to come up with some estimate. They don't have a sense of smell. Does that matter? Actually, it does. Do you know that? Not having a sense of smell, even prior to the pandemic, if you don't have a sense of smell, your chance of dying is drastically higher than if you can smell. True story. So people are like, ooh, that's a lot of money. Let's knock a zero off that. Okay, the actuary's like, all right, your policy is now $91 a month. Okay, you got a deal. And so now you've got $50,000 of life insurance instead of $500,000. That's enough to cover your funeral and a semester at Harvard. So just dealing with much larger scale numbers. Yeah, I've looked at my buddy's study guide for like actuary. It's hard. It's hard. It really is. He was a math major in college. Math CS major. And it was hard for him. So if you lose a sense of smell in the military, it's 100% disability. Wow. Yeah. But your risk of dying if you don't have a sense of smell is ridiculously higher. I don't remember what it is, like twice. Like your relative risk is like twice or something like that. The chance of dying. Okay, so you guys understand? That's life insurance would be an industry where you'd use this. Or you could go into the gambling world. I don't know. Become a underground blackjack dealer or something. I don't know. All right. So, what other probability things do we need to go over? I think we're pretty close to being done with probability. We'll be moving to stats next week. Make sure you do Kearney Castle, not Dino Panic. I pushed that Dino Panic, but Kearney Castle's the one. There's a README file that has the grading scale on it, and what you need to do is go onto Canvas and report which level of completion you did on it to make my grading easier. Interesting. Huh. Interesting. This is a game system a friend of mine made, and yeah, kind of cool. You can probably run through the probabilities of that as well. But yeah, like role-playing games, you know, obviously you need to know probability and statistics for that, for making them, like if you want to do game design stuff. Because there's not just the average numbers. The average numbers are the average numbers, but there's also a sense of fun that is kind of hard to impart in a class like this. But like if you're playing with a roll and keep system, because the tens explode, there's sometimes like this moment of drama where you like hit somebody and you roll your 6 keep 3 and 2 of them are 10s. You're like, oh, double explosion, and you pick up 2 more dice, you roll them, and one of those is a 10. You're like, oh, I got 3 explosions. You roll another 10. Oh my gosh, and another 10. It's like this big moment of drama, and everyone's like, oh my gosh. You're like 78 damage, you know. And so there's always that chance, and it's even worse when it happens the other way, right? A peasant throws a rock at you, quadruple explode, you die. You know, like it can happen. So there's always that tension in L5R that you don't have with Dungeons & Dragons, because in Dungeons & Dragons, when you do a D8 plus 4 damage, you have a very constrained scope of damage, right? A D8 plus 4 will do between 5 and 12 damage every time. Even uniform distribution probability, right? In L5R, there's that big question mark on the high end. Like, there is no high end. What's the maximum roll? Infinite. You know? So a peasant throws a rock at you, there's always a chance that it goes right into your eye and you die. And there is no raised dead in L5R. You're dead. And so it makes... there's an element of tension that that happens in L5R games that you don't get in Dungeons & Dragons. Because, you know, you can... Very often in Dungeons & Dragons just hand wave the combat. You're like, I'm looking at the way the numbers are going. There's no way the bad guys can win. They lose. Done. Move on. So, let's see here if there's anything else we need to go over. PDF, CDF, PDF. Conditional and joint probabilities. Yeah, we do need to talk about those. Ooh, and Bayesian too. What week is it? 15? Got week 16. Week 17. We need to do one more bridges assignment. We gotta do the competency exams. I've been slacking on that. So, okay, we'll do joint and conditional probabilities. That's actually a big topic. We'll do conditional and joint probabilities and Bayesian probabilities. That's actually really, really important. We'll do that on Tuesday, and then we'll move into stats on Thursday of next week. And then Kearney Castle will be due next Tuesday. And then I should have your next Bridges assignment ready on Tuesday of next week. I'll be due the next Tuesday. And then the stats assignment will be due during finals week. And then that'll be it for the semester. Okay. And we'll do some Xi books. And yeah, should be good. And the competency exams, which will be coming up in short order. Yep. Semester is almost over. Yeah, it's kind of crazy. But yeah, and then 45 will be in person next semester, so that's exciting. It'll be good to meet some of you guys, because some of you guys have been teaching for almost 2 years now, and I've never met you in person, so that'll be fun. Yeah, good. Thursday next week is Thanksgiving. Oh, shoot. Then next Tuesday is going to be a long day. All right. Conditional and joint probability will probably be an hour. Then we'll do stats after that. Yeah, it's doable. And while you have the break, then you'll have plenty of time to work on your bridges assignment because you got nothing else to do. Okay, sounds good, everyone. How about some Saturdays? Now, there is going to be a meditation workshop this Sunday at 2 o'clock, and there's going to be a Grand Theft Auto modding workshop 2 Fridays from now, December 3rd, I think, maybe 3. Yeah, 2 weeks in a day from now, there will be a Grand Theft Auto modding workshop as well. Okay. So that's it for today, guys. Thanks for coming out. Thanks for hanging out. I hope you learned a little bit more about probability today and how computer scientists are idiots and we need computers to be our crutch to keep us from crying and not being able to solve problems. So that's the lecture for today. Is that I dumb and so I just use a computer to solve my problems for me. All right. See you guys.